So this screencast is going to focus on the stoichiometry that's in the last part of chapter 3. And we'll start with non-limiting stoichiometry. There's 4 examples in the notes. We'll actually do 2 of those. And I think that'll be plenty kind of to refresh your memory. And then we'll do a couple in the limiting reactants. But basically, some highlights are listed here. Stoichiometry is that strange word, but all it means is the mass relationships between reactants and products. And if we're doing non-limiting stoichiometry first, then we don't have to really stress about who's going to run out, because we either assume we have an excess of the other reactants, or there may just be the one reactant in the first place. So the most important thing to remember is that the stoichiometric ratio comes from a balanced chemical equation. So we've got to be able to write and balance chemical equations, and when we take those coefficients, they become mole ratios. If I want to go from one substance to another substance, the only way I can do that is if they're in moles. And so the mole ratio is really what connects all the reactants and products in a balanced chemical equation. So if we come down here, we're actually going to use BCA tables, which is what we did last year when we did limiting reactants, but they actually work really well for a problem like 85 because they're asking about every single one of these products. They want to know the mass of all 3. We only have one reactant, which is 10.8 grams, and so again, we don't have to worry about limiting reactants. So if we set up a BCA table, if you guys remember, the only thing you can plug into a BCA table is moles. So it must be in moles before you can put it in the BCA table. And then the B stands for before the reaction takes place. So these will all be at 0. The change comes from looking at the balanced chemical equation. So if I wanted to interpret this in terms of moles, I could say 1 mole of this reactant forms 1 mole of this product, 1 mole of that product, and then 4 moles of the final product. So if they've given me 10.8 grams, I need to go over here to the side and get the 10.8 grams into moles. And of course I do that using a balanced chemical, or not a balanced chemical equation. I do that by finding the molar mass. So the molar mass for this is 252.1 grams. So I divide and I come up with 4.28 times 10 to the negative 2 moles of reactant. So that's going to go down here in my before for moles. Alright, and so I know that all this is going to be used up, and then these will be formed. So this will go down by x, this is going to go up by x, this will go up by x, and this is actually going to go up by 4x. And if you remember, x is equal to the moles of limiting reactant. Well, again, in this case, we only have the 1, so we don't really have to worry about that. X is going to mean that all of this gets used up. So x is equal to this guy right here. So this will be gone. This will be 4.28 times 10 to the negative 2. This will also be 4.28 times 10 to the negative 2. And then this is going to be 4 times 4.28 times 10 to the negative 2. Alright, so they did want masses, so now I'm going to have to change all of these to masses. The molar mass for the Cr2O3 is 152.0 grams. The molar mass for N2 is 28.0 grams, and the molar mass for water is 18.0. So I won't show that bridge, but you basically multiply the moles times the grams per mole, and you'll get, let's see, 6.51 grams for the chromium oxide, 1.20 grams for the nitrogen, and 3.09 grams for the water. So again, I like the BCA table. If you don't like using a BCA table, you could certainly set up, 3 different bridges, but I think inevitably it does end up taking you more time doing it that way. So hopefully you like the BCA table and it's a good way for you to work out problems. So we're going to skip 87 and 89 and jump down to this last one. So it's cisplatin, and it's an anti-tumor agent, and they're showing you how it's synthesized. And I like this problem because it's giving you these compounds that you've never seen before. And that's what College Board likes to do on the AP exam. They like to give you a balanced chemical equation that looks scary, but honestly, if they've given you an equation, you can either balance it or they've balanced it for you. Don't stress about how complicated it looks, just work through the problem. So here we're starting with, and I'm just going to kind of move my BCA table to save time. So 100 grams of this K2PtCl4. And I'm going to change that into moles so that I can figure out how many moles I have to work with. Now, it says sufficient NH3, which tells me I don't have to stress about how much NH3 I have. So there's my molar mass. So I've got 100 divided by 415.3. That gives me 0.241 moles. So to begin with, I have 0.241 moles. They want to know how much cisplatin, so this guy, can be made, and then what mass is also produced. So again, they're asking about both. So the BCA table actually gives you a nice picture. So this will go down by X. This I don't have to worry about because it's an excess. So I'm just putting EX there. This will go up by X, and then watch your coefficients. This will go up by 2X. So this will be all gone. I'm going to have some of that left over, but that doesn't matter. And I'm going to make 0.241 moles of the cisplatin, and then I'll make 2 times 0.241 of the KCl. So I've got my moles. They wanted a mass, so I've got to get that into grams. So the molar mass for the big guy, let's see, is 300.1 grams, and the molar mass for the KCl is 74.6 grams. So you end up with 35.9 grams of the KCl and 72.3 grams of the cisplatin. So hopefully that is a pretty simple refresher on non-limiting stoichiometry, so you don't have to worry about who runs out of. When we do have limiting reactants, and they won't always say, hey, remember to test for limiting reactants, you just have to know that if they give you 2 amounts of reactants, then you've got to test to see which one runs out. And so to do that, just to refresh your memory, you get both of your reactants into moles. So in this example, we've got mercury and bromine, making mercury bromide. They've given me 10 grams of mercury, 9 grams of bromine. Please don't be fooled into thinking, oh, that's less, so that's going to be our limiting reactant. It depends on mole ratio, and it depends on molar mass. So the first thing we have to do is come up to the side and figure out how many moles of mercury I have. So mercury's molar mass is 200.6 grams per mole. And let's see how many that gives us. 200.6. So 0.0499 moles of that. And then our bromine, our Br2, its molar mass is 200.6. Nope, they can't have the same molar mass. Just kidding. Br2, let's see, 79.9 plus 79.9, 159.8. Sounds better. So 9 divided by that. So I've got 0.0563 moles. Okay, remember, I don't just take the lower number, I divide by the coefficient. But in this case, they both have a coefficient of 1. So I divide by 1, and who's my limiting reactant? Hg. It's going to be limiting. Alright, so if I do my BCA table, I've got 0.0499 moles of that, 0.0563 moles of my other reactant, and 0. So this will go down by X, up by X. Okay, well X, which one is it? It's going to be this one because that's my limiting reactant. So this one will be all gone, and then 0.0563 minus 0.0499, that leaves me with 0.006, not a whole lot, and then this goes up by X, so 0.0499. So these are all moles. So the question was, what mass of HgBr2 can be produced? So I've got to get this into grams, because this is my HgBr2. And so that molar mass is 359.8 per 1 mole. So 0.0499 times 359.8 gives me about 17.95 grams. So actually that should be 18.0 grams. And then it asks what mass of which reactant is left over. Well, this was our excess reactant, our Br2. And so if I have 0.006 moles of Br2, now I'm going to say times 159.8 grams per mole. So 0.006 times 159.8. So that gives me 0.9588. So really 1 gram, and not even with that because of sig figs. So just 1 gram left over. So that's how you use a BCA table when you've got 2 reactants, both given in grams. You've got to figure out who's limiting, what your X is, and then solving for your product. Alright, so B is a follow-up question given to you a little bit differently. It says, well, if you have 5 milliliters, they were nice and gave you the density, and then 5 milliliters of bromine also gave you the density, now how much HgBr2 can be formed? So a similar question, but a little bit more work because we've got to work from our density, which isn't super difficult, but it certainly adds a twist. So let me write the reaction out so we can do our BCA table later. Alright, and then off to the side, I'm going to figure out, let's see, our mercury first. So the density is 13.6. We know that density is mass over volume, and we have 5 milliliters. So my mass of mercury is 68 grams. And I only have 2 sig figs on that. Let me check why. 13.6 times 5.00. 60. I'm not sure what's up with that. 13.6 times 5. So it should be 68.0. And then for our Br2, similar story. The density is 3.1. I'm looking for the mass, and the volume is 5 milliliters. And so 3.1 times 5, 15.5 grams. Okay, so now I've gotten basically to the point I was given in this problem. So a little bit more work to get to the mass. And now I've got to figure out how many moles that is. So I'm going to divide this by the molar mass of the mercury. And that gives me 0.339 moles. And then I'm going to divide this by the molar mass of bromine. So 15.5 divided by 59.8. That gives me 0.0970 moles. So again, we don't pick smaller until I've divided by coefficient, but again, the coefficient's 1. So I divide by 1, divide by 1. This time, bromine is actually my limiting reactant. Alright, so if we set up our BCA table, I've got 0.339 only moles go into your BCA table. Don't ever try to put masses or anything else. And this is 0. So this is going to get all used up because that's my X. This is going to go up by X, and this will go down by X. So we'll be left with 0.242 moles of mercury. All the bromine will be gone, and we'll produce 0.0970 moles of the HgBr2. So this asked about the mass, so we'll go ahead and convert this to a mass, and our molar mass was up here, so 359.8 grams per mole. Alright, so that's going to give us 34.9 grams of our product. Alright, so hopefully this was a good refresher from first year chemistry on both the non-limiting and limiting stoichiometry, and that'll give you some guidance for doing your problem set.